Consider a series like the following. I have the sum from k equals 1 to infinity of the sine of k divided by k squared. The key thing I want to point out here is that this series has negative terms, and it also has positive terms. But importantly, it's not an alternating series. And remember that in order to be alternating, it has to alternate in sign every other term. If you think about the sine of k, there are going to be successive terms that are positive, positive, or negative, negative, and so that will make it not alternating. So it has negative terms, which means that it rules out me being able to use the integral test, the comparison test, or the limit comparison test. It's not alternating, so I can't use the alternating series test. The terms approach zero, so that rules out the test for divergence. It's not geometric, it's not telescoping, so we're kind of getting to a point where nothing we've seen thus far actually applies for this. So when we encounter series that have negative terms, a new thing that we can start to think about potentially applying is what's known as the absolute convergence theorem. So this theorem says that if you know that the sum from k equals 1 to infinity of the absolute value of a sub k converges, then it must be true that the sum from 1 to infinity of just a sub k converges as well. So one thing I want to point out here is, again, a common mistake. And that is referring to the other direction. So this is not an if and only if statement. So this kind of goes back to when we talked about logic. So I'm saying in some sense, A implies B here, and it does not necessarily mean that B implies A. So a good way to keep that in mind is to think of a series we've already looked at, and that's the alternating harmonic series. So if you recall, that was the sum from 1 to infinity of negative 1 to the k minus 1 over k. This series converges. So think about this as playing the role of a sub k. If you then wanted to look at the sum of the absolute value of a sub k, that would simply be the sum from 1 to infinity of 1 over k, but that's the harmonic series. This we know diverges. So we see here an example where the sum of a sub k converges, but the sum of the absolute value of a sub k diverges. And the moral of this is just to be careful that this doesn't work in both directions. But what we're saying here is that if the opposite holds, if the sum of the absolute value of the terms converges, it must be true that the sum of the original terms converges as well. So let's go back to our starting example to see how that would help us there. So I'm looking at, again, recall the sum of sine of k divided by k squared. What I can take advantage of is if I can show that the sum of the absolute value of these terms converges, then I can use the absolute convergence theorem. So what do we gain by taking the absolute value? The main thing we gain here is that we now have a series with all positive terms, the one that I'm writing in this bottom line here. That now allows us to use some of the tests that require positive terms. In particular, because the sine function is always less than or equal to 1, I can bound this above by 1 over k squared, this series. So we know that this series converges. It's a p series where the value of p is 2, which is strictly greater than 1. So that means that the sum of the absolute value of sine of k over k squared converges, and it's important here to say why. What we're using in the line above is the comparison test. But we're not done, because our original intent was to look at the sum of the terms without the absolute value. But now we know that if I were to put the absolute value around those terms, the series converges. So this is enough for me to say that the original series converges, but I have to reference the absolute convergence theorem. So one thing I'll point out here that's going to be useful as we move along, when using the absolute convergence theorem, it's always coupled with something else. For us, that was the comparison test here. So we need to justify why it is that the sum of the absolute value of A sub k converges, and then come back and finish off the statement by referencing the absolute convergence theorem. So there's several things we need to do to kind of justify our final conclusion. This brings us to a point where we can talk about different kinds of convergence. So to begin with, if I think about the collection of all series, so far we have divvied that up into convergence and divergence. So what I want to define now is different kinds of convergence. And it didn't make sense to talk about this until we started looking at series that had positive and negative terms. So a series, let's just call it sum of the A sub k's, we're going to say converges absolutely if the sum of the absolute value of A sub k converges. And I want to point out that that automatically means that A sub k converges. We're just further calling it absolute convergence. And again, that automatic implication is the absolute convergence theorem. So that's what it means to converge absolutely. And alternatively, we're going to say that a series, again, sum of the A sub k's, instead converges conditionally if the series itself converges, but the sum of the absolute value of the terms diverges. So these definitions are very important, and I think a lot of times it takes a little bit getting used to the distinction between those. Coming back up to my Venn diagram, I want to be clear here that we still have the two kind of original subsets. So I have convergence on one side, and we have divergence on the other. What we're doing now is we're taking our set of all converging series, and we're further breaking that up. So we still have convergence, but now there's absolute convergence and there's conditional convergence. We're not further refining diverging series. There's still just one group of series that we call diverging. So it depends on what the question is asking in terms of whether or not we need to distinguish between absolute versus conditional convergence. We'll still encounter examples that simply ask, does the series converge or diverge? In which case you don't have to specify what kind of convergence. A couple things here to point out. Let's see back here. So we haven't mentioned this refinement of convergence yet, and I want to point out a series with all positive terms, like many of the ones we've already seen, either diverges or converges absolutely. And to think why, if the series has all positive terms, then these two sums are exactly the same. Those only become different when I have negative terms. So when we've been talking about convergence in the past, it's typically been what we're now going to think of as absolute convergence. This question becomes interesting when we start to look at series that are not simply consisting of positive terms. As a quick example, again, to distinguish between these two types of convergence, one series we've focused on is the alternating harmonic series. So -1 to the k minus 1 over k. This series converges conditionally. Again, for reference, we've already looked at that without that terminology up here. We said that the series itself converges by the alternating series test. And then in the second line, we looked at the sum of the absolute value of the terms. That led to the harmonic series, which diverges. That's a perfect example of conditional convergence. However, if I made one very small change, if we look at the alternating series with terms -1 to the k minus 1 over k squared, this series converges absolutely. Like the one above, we could use the alternating series test to look at the original series, show that that converges. If you take the absolute value of the terms, you're going to end up with the p series 1 over k squared. That p series converges. So because both of those converge, that leads to what we call absolute convergence. Now, it does take some practice, again, to get used to being able to determine absolute versus conditional convergence, especially if you have a more complicated series. We're going to have a whole video devoted just to going through examples where we look at that. One last thing I want to throw in here that relates back to the alternating series. First of all, if we have, let's see, in our alternating series example, let me backtrack here. There we go. So when we talked about identifying an alternating series, we were looking for things like -1 to the k, -1 to the k minus 1. Something I often see is people kind of gravitating towards seeing that in any type of series and assuming that it's alternating. So I just wanted to point out here, seeing something like -1 to the k doesn't always mean you should use the alternating series test. So for one, if I have the sum from 1 to infinity of -1 to the k plus 2k over, k plus 3. Notice that, of course, there is a -1 to the k in here, but importantly, it's not being multiplied by 2k. And what that means here, if you were to start writing out the terms, is that you'll find that this is not alternating. This has all positive terms. So in this instance, you can't even use alternating series test. One of the assumptions in using it is that you do in fact have an alternating series. If I also have something like the sum from 1 to infinity of -1 to the k over 2 to the k, this is alternating. So it would be completely justified to use the alternating series test. However, that doesn't mean that you have to use the alternating series test. Notice that this is also the same thing as -1/2 to the k for these terms. This is geometric. So arguably, it would be even quicker to simply reference the fact that the r value here in absolute value is less than 1 and quickly say that it converges. The other advantage to noticing that this is geometric is that you could find the series of this, the sum of this series, which you can't do with the alternating series test. And I'll finish off, or you could use the absolute convergence theorem here. So there's just other ways that you could go about verifying that something like this converges.